let me summarize quickly on accelerated computing. If you take a look at some of the results that I've shown you, it is very, very clear that as Moore's Law comes to an end, that accelerated computing is really a wonderful path forward. And it's a wonderful path forward because of the architecture, because of the system software stack, and because of the domains that we've selected, and the fact that we work across each one of the applications middleware and the architecture in an iterative basis. And over time, you can see that the results continue to compound. On the left is Amber performance, molecular dynamics. On the right is GoogleNet, deep learning. In both of those examples, we continue to advance. I want to now talk about AI at the edge. I've got some delightful things I want to share with you. I'm going to go quickly. You guys know that we're really dedicated to the automotive industry. And the reason for that is we believe that everything that's going to move someday will be augmented by autonomy. Everything that's going to move someday is going to be augmented by autonomy. We're enjoying, as you know, the Amazon effect. As we every single day buy things, don't forget, we used to drive to the store to pick up things, but now we expect the things to come to us. The number of truck drivers, the number of transportation professionals can't keep up with the Amazon effect. And so we have to find a way to automate as much of that entire path as possible. Augment it, take pressure off of the drivers. The number of truck drivers, for example, in many countries is short by about 50%. And so we need to find a way to automate some of this so that we can keep up with the Amazon effect. Not to mention, society could be much, much more beautiful, and our environments could be much more beautiful if we didn't have so many parked cars. Very few of us would remember that for every car that we own, there's actually 3 parking spaces created for us, not even including the one we already own. And so there are 800 million parking spots in America. There's only 250 million cars. And it makes a lot of sense because we just never know when we need it. Okay, so I think vehicles, transportation, will be augmented by autonomy in the near future. We've created a platform we call the NVIDIA DRIVE. And basically, it's a roadmap. It's an architecture that spans level 2 to level 5, from augmented driving all the way up to completely driverless systems. We created a full stack. We dedicated ourselves to go solve the self-driving car problem and create the software stack, but open up the software stack. To create the software stack, understand the problem deeply, but to open it up. And keep it open so that hundreds of people can use it. We now have 200 developers around the world using Drive PX. They're startups, they're shell companies, they're car companies, they're trucking companies. We have wonderful partners in Bosch, the largest tier 1 in the world, ZF, the largest trucking tier 1 in the world, PACCAR trucking company, all the startup companies that I mentioned earlier today. It's all possible because the Drive platform is open. And it's open on so many different levels, you can intercept it at any level that you desire. Let me show you a couple of videos of what it can do, and then I got a big announcement I'd like to share with you. And so the first thing is this. The first thing I'm going to show you is mapping to driving. Basically how the car figures out where it is in the world and localize within it and detect everything that's around it and drive. The second thing that I want to show you is how we use AI not just for driving, but also to be essentially a virtual co-pilot. And third, this is a phrase that Gil Pratt at Toyota created that I really, really love, and it's called a guardian angel. Even when you're not driving, even when the car's not driving for you, even when the car's not driving for you, it should be watching out for you. And so the AI is on all the time, even if it's not in autonomous vehicle mode, it should be watching out for you. So let me show you a couple of videos. The first one is mapping to driving. And so in this particular case, the first thing that's happening is we're using the LiDAR. We have a LiDAR mapping car, and we're trying to detect everything that's around us, whether it's the lanes, the vertical poles. We're trying to create essentially an HD map of the structures in the world that we ought to use to localize ourselves later. Okay, so we detect all the road features. We construct the HD map. There are amazing companies who are doing this. We create the middleware, and there's a great company called DeepMap who does this, and of course TomTom does this, Here does this. Mapping company, we're partnering with mapping companies all over the world, and now we put that into our car, and it's in autopilot mode. Notice it's detecting the cars around it, it's detecting the lanes, detecting all the signs, and now you have confidence that the BB-8 is driving safely in the road. okay? And the next one is Copilot. This is our own Janine.
I can now drive you to work based on mapping previous drives. Shall I engage autopilot?
Oh, sure.
Autopilot engaged. Driving to work.
Janine is in our marketing department, and she's also one of our test drivers. She's very, very brave. And so, beautiful and brave. All right, so she has the benefit of a co-pilot there, and basically what's happening is this. Of course, we're not going to have the whole world mapped. And we're going to map the world as fast as we can, and wherever it is mapped, the car should know. And it just lets her know that, hey, gosh, I could drive the car for you now. Would you like me to take over? And the next, let me show you Guardian Angel. There we go, green light, time to go. Whoop.
Cross traffic danger.
Maybe not.
All clear.
Disaster averted. Okay? And so this is possible because the car sees everything around it all the time. Well, we have partners, as I mentioned, 200 partners around the world. They're startups, they're shuttle companies, they're even Airbus creating a self-flying plane that they would like to make available in the year 2020. It's a VTOL, takes off by itself. It occupies the space of 2 parking lots, and it's for 2 passengers, and it'll go 70 miles. I can't wait for this. This is incredible. And so Airbus is creating an autonomous airplane. They're a Dutch company using our platform for autonomous ships. There are companies who are using our platform for autonomous pizza delivery. And so keeping this open, creating an open platform, AI computer that everybody can use has proven to be incredible. Well, today I'm just incredibly honored to announce that Toyota has selected NVIDIA DRIVE PX for their autonomous vehicles. As you know, Toyota is one of the largest companies in the world. I believe they're the 9th largest company in the world. They have 350,000 employees. This is a company that is legend in so many different ways. So much of modern management has come from Toyota. Kaizen, continuous improvement. Genji Genbutsu. I bet you guys didn't know about that one. Go to the source, see it yourself before you come up with a solution. Just-in-time manufacturing. The pull model of manufacturing, not push. So many of modern management systems were invented by this company. It's an incredible company. They dedicate themselves to the highest level of safety. So they're working with us, and the 2 engineering teams are now working incredibly hard together to create their autonomous vehicle car. And we'd like to finish it and put it on the road in the next few years. We would also have a mutual goal, a combined goal of achieving 0 fatality someday. And so this is going to be their architecture for their future production cars. I'm super excited about that. Ladies and gentlemen, Toyota on DRIVE PX. The processor inside this Toyota machine autonomous machine will be the Xavier. Some of the things that's really cool about this is this. A lot of people are surprised. How is it possible you guys could put 30 trillion deep learning operations in 30 watts? Well, the reason for that is this. And this is a question that's come up a lot recently about accelerators and TPUs and FPGAs. Basically, the way you think about these processors, the CPU and the FPGAs are general purpose. They could almost do anything. You can make a CPU, you could write any software for it. You could use an FPGA to do any video decoder, Ethernet chip. You could make it do almost anything. The flexibility of these 2 architectures comes with it the cost of efficiency, the cost of efficiency. The next 3 processors, 2 CUDA GPUs, one is Pascal, one is Volta, and the last one, the one on the bottom, is called a DLA, the DLA, Deep Learning Accelerator, what some people would call, for example, a TPU. they are specialized in their domains, and so therefore, they tend to be much more energy efficient, they much more performant within any constraint, I've already talked about how CUDA has been improved with the Tensor Core, and so Pascal's level of deep learning capability, although great, is now enhanced by Volta. You could take that even further. You could create a custom ASIC with, we call the DLA, and you can improve the energy efficiency by another third. Okay, you can improve it by another third. And so this basically gives you a landscape of all the different processors in the world. For our data center products, we need it to be flexible. We need to be able to run almost any network that comes our way. And so the flexibility of CUDA is too valuable for general purpose computing platforms, for data center platforms. However, in the case of Xavier, we've done something very special. What we've done is we've created a processor out of these three. In order to drive, you still need to localize, you need to reason about where you're going, you need to plan, and the planning process is highly parallel and requires 32-bit floating point processing. And so we decided that we would use CUDA for that. We also know that there's all kinds of interesting networks that we are about to deploy, not just computer vision object detection networks, but much more sophisticated networks for the future, and we need programmability for that. And so Xavier includes the CPU's single-threaded performance capability, CUDA's flexible parallel acceleration capability, and it also includes a deep learning accelerator that provides for specialized functions in computer vision. Well, the thing that's really great about this is now we have an architecture that is both programmable, super energy efficient, robust for all kinds of networks that we can come our way, can run the entire software stack of self-driving cars. And as we were thinking about building this, we realized that there are so many companies in the world who would value having the ability to create a deep learning accelerator. We understand this space so well because we understand the entire pipeline. We understand the entire pipeline from the beginning of the creation of the network all the way to deploying it into any environment. We understand and we have the software stack across the board. And so what we decided to do was realize that, gosh, it's so incredibly hard to put all this stuff together. Why don't we accelerate the adoption, democratize deep learning, lower the barrier of entry for every single of the trillion devices in the world that someday that will use deep learning. We're not going to build them all. However, we would like to see adoption to accelerate for all of them. And so, ladies and gentlemen, today we're going to open source the Xavier DLA. The best engineers in the world are working on the deep learning accelerator. We're going to take this accelerator, what some people call TPU, and we're going to open source it. And you can continue to follow our instruction set, or you could decide to change it. If you adopt ours, we'll continue to support it with software. If you decide to change it, it's no big deal either. Okay, it's completely open source. We're going to early access it in July, and we'll have general access in September. Our goal is proliferated.